Hi everyone. In this video, we're going to remind ourselves of the theory of inverse functions and talk about how that can help us build more anti-differentiation techniques. To motivate this topic, let's remind ourselves of some things that we learned recently. We know that every proper rational function can be written as a sum of partial fractions. And you should remember that the reason why that's important is because it allows us to find antiderivatives of rational functions more easily. In fact, if we had a general method for anti-differentiating partial fractions, then we would know how to anti-differentiate every single proper rational function that we ever want to. So integration of rational functions really only boils down to two problems. We need to know how to integrate the constant over linear type of partial fraction, and also the linear over irreducible quadratic type. If we could just figure out how to do these types of integrals, then the entire problem of integrating rational functions would be solved. This first type is actually relatively easy with the tools you already know, so consider a typical example like this one. All you'd need to do here is perform a simple substitution where u equals the linear function, and since the derivative of a linear function is always a constant, the calculation of du is never going to cause you any problems here when you do that. And so the remaining details are basically always going to work out nicely. This other type of integral, though, is hard in general, and you don't have the tools yet to handle these, but we'll be developing them throughout really the rest of the course. The conversation about how to handle these starts with the theory of inverse functions, and hence why that's the topic of this video. In particular, we're going to need to consider the inverses of exponential and trigonometric functions, so that's a preview of what we'll be studying for the next little while. Let's quickly remind ourselves of some of the basics. Inverse functions can be defined as functions which undo each other, or to put it another way, they cancel each other out. So more precisely, let's say you had some value of x, and if you applied the function f to it, the output is what we usually call f of x. If you then applied the function g to that output, it should cancel out the effect of f, so you should get back the same x that you started with, as you see indicated by this diagram. But to put that in symbols, if you started with x, then applied the function f, and then applied the function g, if f and g really are inverse functions, then f and g should cancel each other out, so the result of this should just be x. We should also observe the same thing if we applied these functions in the opposite order. So if you started by applying g and then applied f, the result should still be the same x that you started with. So in symbols, that means f of g of x also equals x. Since these two equalities capture the idea of functions canceling each other out, these can really be taken as the definition of inverse functions. Let's look at an example. Show that the inverse of f of x equals x plus 3 is what? Well, f of x is a function that adds 3 to its input. So I'd expect the inverse to be something that does the opposite, subtracting 3 from its input. So this should make sense intuitively that the inverse function would be x minus 3. But to actually prove that these functions are inverses, we need to respect the actual definition rather than just making these assumptions. So let's calculate these quantities. We can see that g of f of x would just be another name for g of x plus 3. And that's found by looking at the formula for g and just plugging in x plus 3 wherever we see an x. The result of that would be x plus 3 minus 3, and sure enough, that's just x. Since g of f of x equals x, we've verified the first part of the definition. A similar argument can be used to verify the second part, and you can pause here to check the details if necessary. In high school, you should have seen that the inverse of f of x is usually called f minus 1 of x, as you see here. Although this notation is commonly used, it's also really misleading because it gives the impression that there's an exponent of -1 here. But this is actually not an exponent. It's just a notation that we use to indicate the inverse. It just happens to look a lot like an exponent. If I wanted to indicate an exponent of -1, I would indicate it this way instead as f of x all raised to the -1. You know, an actual exponent of -1 like this would indicate taking the reciprocal of my function, but in general, the reciprocal is not the same thing as an inverse. So be cautious of these two notations that look really similar, but actually have completely different meanings. Another important concept relating to inverse functions is the horizontal line test, which I'll abbreviate as HLT. You should know that not all functions have an inverse. In fact, the only ones that have inverses are the ones that pass the horizontal line test. And that just means that no horizontal line crosses the graph more than once. This is something you've probably heard before, but the time has come where you need to start being an expert in these concepts rather than just being familiar with them. So instead of just stating this as a fact, let's see if we can understand and explain why this is actually true. The key is to remember what inverse functions do in the first place. If we think of x as the input and f of x as the output of our function, then by definition, f inverse sends that output back to the input that it came from. In other words, f inverse of x returns each output back to its corresponding input. But let's imagine a situation where f of x actually fails the horizontal line test. So take this curve, for example. Because the horizontal line test fails, we can see a y value that corresponds with multiple x values. Or in other words, there are some outputs that correspond to multiple inputs. So the inverse function wouldn't know which input to return, or in other words, which x value to return. And that's why we can't have an inverse function unless the horizontal line test passes. Another thing you should remember is that if an inverse function does exist, it can be found by interchanging x and y. And that's because what an inverse function literally does is interchange the roles of inputs and outputs, and those are what we call x and y respectively. So for example, let's consider the inverse of the function y equals x squared plus 3. Something I hope you noticed right away is that this function doesn't pass the horizontal line test. So actually we can't find an inverse with the question as stated. For that reason, it's common to place a domain restriction on a function so that an inverse can be found. So in this case, our domain restriction would throw away half the parabola, leaving us with a function which will now actually have an inverse. So to find that inverse, we need to now interchange the x's and y's. That would give us x equals y squared plus 3. Just be mindful that the interchanging of variables also applies to the domain restriction, so that now becomes the restriction y bigger than or equal to 0. Now we can go ahead and solve for y with a bit of basic algebra, which would show us y equals root x minus 3 as our inverse function. Be careful though. Anytime we take the square root on both sides, we should be considering the possibility of a plus or minus sign. And in general, I would expect you to show that you've thought about this. In this scenario, since we know the y values of the function can only be positive due to that restriction, we can throw away the negative case. And so the positive case is the one that we declare as our final answer. So that's just a quick refresher of the basics of inverse functions and how they're going to help us with anti-differentiation techniques. We'll continue the conversation in the next video, so look forward to that, and I'll see you next time.